Well, he's leaving too, but he's leaving. But one of them's leaving for India. I just got here. No, I just happened to grab it. I forgot. Not for you. Oh shoot, you're gonna join us? I joined last night. Stay with her. Oh, I turned it in already. Did you expedite your membership? No. Give it online. It takes like. That's what mine was like. Oh, she says it's approximately 33 minutes. Instead of 30 minutes. She said 33.
Pull it outside. You don't even know they do that.
All right. Good afternoon. Welcome back. Okay, so any questions at this point? Any things which are still kind of not clear? Okay, seems like we have a blast. Oh, Ben.
If I'm registered for the Tuesday lab on Telebears, but I wanted to be in the Monday lab, and I wrote Monday on the sheet.
Okay. I don't care about Telebears whatsoever for labs. Have your name on there somewhere. It's important. But now the important thing, as I mentioned, is show up. I looked at the distribution as people signed up, and we're fine. So show up at the day you want to pick. And as I said, sign up. We're going to have sign-up sheets that day. You're going to have to enroll in that lab at that day. And then you stick to it. Don't start changing your mind halfway the semester. That makes life miserable for everybody. Now, just pick the one right now and show up next week. And that's the selection procedure. Just signing up, or just showing up. Okay? Any other questions? There was a little bit of a problem with the homework. I saw that a number of you had a little bit of problems with getting the simulation to do anything reasonable. And there had been some small correction broadcasted to all, basically on. It was mostly the ground selection, the ground signal and the VDD signal you used. So there was some problem with that. Okay, let's see. So labs begin next week. So as I said, show up. Homework 1 is due 5 o'clock today. Remember 2:40. We'll finalize on that, 240 Corey Hall. And we'll post probably somewhere later this afternoon, in the evening approximately, we're going to post homework number 2. Homework number 2 is going to be doing a couple of things. Mostly going to look at metrics, trying to do some VTC analysis of some idealized devices. Some propagation delay computations, kind of see if you still remember how to do a differential equation or simplify a differential equation. And then some simulation problem. We're going to play around with some of the, as I mentioned before, I think this class we're going to use 90 nanometer transistors. So we're going to play around a little bit with those transistors, getting some properties of those 90 nanometer transistors we can use in this class extracted. Like for instance, what's the threshold? How does the threshold vary? Things like that. Okay. All right. No other question. Everything's crystal clear. Things are still quite straightforward so far. It's going to get. We'll ramp it up a little bit later, but step by step. So let me know if there's anything that you are concerned about in terms of speed and things like that, so we know it's going to adjust that. I mentioned at the end of last class that next week there will be this conference in San Francisco, which is called ISSCC. It's the International Solid State Circuit Conference. It's the biggest event in circuits. If you're really kind of a circuits person, this is the thing to go to. It has typically about 3,000 people showing up and has a whole selection of papers, lots of papers in a number of areas. It goes from digital, advanced memories. Every year you see the latest flash memories coming out. What's going to be the things that you're going to see a couple of years on the market, later on the market. But also a lot of mixed signal, analog, and RF circuitry. RF actually is the biggest growing section of the conference. Now, every year, however, it's the kind of the big chips that get the most attention. So I just took this from EE Times a couple of days ago, where they kind of had a summary of the key highlights of ISSC this year. It's kind of interesting to look at it. They mostly talk about processors. Processors still kind of speak to the imagination, I would guess. So there's 2 classes of processors that are going to be announced this year at the conference. One class of processors is this kind of big macho quadruple core type of things that are typically used in servers. Not the things you're going to put in a laptop, because like the Intel part, I think consumes 170 watt. So your battery of your laptop would go drain quite rapidly if you put a processor there like there. And that definitely would not be cool to the touch. So these are kind of things you would put in Google servers or the big machines you put for run large programs, right? So it is kind of interesting. Intel is coming out with a new version of Itanium, which is pretty impressive. It has it's a quad-core chip that has what is it? 2.05 billion transistors. And it clocks, I believe, at about 2 gigahertz with 30 megabytes of cache on the chip. It's a big chip. I see the area is there somewhere on there. It's a huge area chip. It's not going to be a cheap one, for sure. Let's see what's the area. It says somewhere. It must be the Sun one is. It must be on the top somewhere. 4 processors. Yeah, I'm trying to find it. It might be, it's on the second, no. Yeah, 700 square millimeters. So 700 square millimeters, take the square root out of that, that's about 20, almost 2.5 centimeters on the side. That's a chip that big. That's a big chip. As I said, that's not going to be a cheap chip either. Yeah, this is definitely intended for this very expensive type thing. But it's interesting that at the same time, Sun is coming out with a new processor, which is getting a lot of attention. Intel is more of the old stuff, right? It's your traditional x86 architecture, just 4 processors, make them a little bit faster, put some more cache on the chip and things like that. Sun is a different one. It actually has 16 processors on the die, and uses a very different interprocessor communication architecture based on something which is called transactional memory. People have been talking about this quite a while in academia. transactional memory and transactions-based processing has been quite popular in academia, but this is the first actual commercial chip that's coming out based on that particular paradigm. So it's a bet. It's going to be interesting. Now, interesting is you look from a performance perspective. People predict that we'll have approximately the same performance. However, the Sun chip is a lot smaller than the Intel chip, which is the Sun chip is about I think it's somewhere up there is 396. That's 400. That's 2 centimeters. So yeah, it's not humongously smaller, but still it makes quite of a difference. And it runs at what? 65 nanometer. Exactly. Both of them are 65 nanometers. Yeah, both Aquila and Rock are in 65 nanometers. So it's kind of interesting to see how different trends are happening in the microprocessor space. Now, in the more low power processor space, there's some interesting entries there as well. Again, Intel is coming out with a new processor called Silverstone, which is a x86. It's not 170 watt, but it's only 2 watt. And it's Intel's attempt trying to move into the smart mobile devices, right? Your little cell phone that has some brains to it, kind of idea. So, however, first, if I would look at it, you say, well, gee, it's 2 watt. Well, that's actually a lot of power from a mobile device perspective. If I take a look at a standard mobile, like your BlackBerry or your iPhone or whatever that, overall power dissipation that we're looking at for one of those devices is typically about 3 watt. And you look at this size factor, you have so much battery, you figure out you want to run it for a week in standby, you want to have so many hours runtime or speak time or whatever you do. So you're counting about 3 watt. Now if you already consume 2 watt of that in the processor for doing like your nice applications and your little gaming stuff and all those kind of things and running your MP3 things, that's a lot of the budget. It means they have very little left for the radios, all those radios that are in there, and doing your Bluetooth and your Wi-Fi and your cellular and your GPS and your AM, FM and whatever you want to have on there. So there's very little left for that. Plus there's very little left also for graphics processing. If you want to add a general purpose graphics processor like an NVIDIA chip to that, your total budget is toast. So that's why people say, gee, 2 watts seems like nice, but it's not very good for that particular market. What else do we see is that at the same time we see some other companies coming out with cellular chips for the cellular phone, like TI is coming up with a completely integrated chip that has every function from baseband processing for the radios all the way to application processing. It has a DSP processor in there, has an ARM processor in there, all on the same chip. Somewhat more dedicated towards the mobile market because it really has some specific components on there that really try to drive 3G cellular telephony and so on and so forth. But it's interesting that how the different entries come into this space. Intel obviously is a general purpose computing company, comes from that end. TI has always been driven by the cellular communications world, so they come from that end. Qualcomm also is presenting a chip which is very interesting as well, again based on the ARM. So there's a lot of activity in the mobile space, and that's a good reason why. It's the fastest growing segment of the market. If you can sell 1 billion cell phones per year, that's a good number, right? That's if you just think about it, that's way more than the number of PCs that are being sold every year. So getting a hold in that market is going to be quite interesting. So it's just a little snapshot. There's a whole lot more stuff. As I said, there's a lot of wireless stuff going on, a lot of interesting analog things, also ultra-low power digital, and then some bizarre stuff too, using some of those newer nano devices. There's some exciting stuff going on in that space, really super scale devices. It's always kind of the biggest show of the year. If you want to, if you're interested in circuits, it's always the place to go. All right, good. Let's go back to the ground. Before we go to basically chips with 1 billion transistors, let's try to do an inverter with 2. So it's backing up a little bit, but you'll see we'll quite rapidly go to more than 2 transistors. So don't worry about that. So this is where we are. Last class I kind of gave, oops, let me just change that. I have to. Last class I gave you a intro to the, okay, let's go back here, okay, to the CMOS inverter. very simple one. So a CMOS inverter is really a complementary pair of devices. Push-pull, there's always one on, one off in steady state. During transition, obviously, both of them are temporarily on simultaneously. But having this push-pull, you either pull it up to VDD or you pull it to ground. That's the whole idea. Okay? And we started talking a little bit about the manufacturing process. What I'm going to do is finish this up first today, talk a bit more about manufacturing. And then I'm going to say, well, gee, that's kind of nice, but from now on you can forget most of what you learned about the manufacturing process, because as designer, typically you don't worry too much about that. What you worry about is, how do I interact with the fab? What do I have to give those guys to basically get my design out? Yeah, so we talk about it abstractly. We're trying to abstract the whole fab away into a number of what we call layers that we have to design. And design rules are an important part of that. And every layer in the design process, we're going to have a set of rules of what you can do and you cannot do. And if you follow the rules, you're a nice person, you don't try to cheat, typically your design is going to come back as it's going to work. If you do simulation right and everything like that. This is what design rules really are. It's a contract between you and the fab. The fab says, if you do it that way, well, we're going to give you a reasonable chance for making it to work. If you try to put things a little more denser, it might fail. Okay? So that's the way these things work. So it's quite nice, because now I don't have to worry about those many layers of the process and all this kind of things anymore. And then I'm going to start rolling a little bit into MOS transistors. So we're going to start talking about models of MOS transistors. And I said, again, in this class, I'm not really interested in how exactly the transistor operates. I just care about the model that basically I will use. So it says, how can I model the behavior of that transistor in such a way that I can make my digital design work correctly? And then I can forget about all those electrons and holes flying around. I don't worry about those things too much. I just care about the model at large. Okay? So all of this comes directly from the textbook. So chapter 2 and chapter 3. Let me just recap briefly the end what we discussed in last class. An inverter is basically two resistors that play against each other. So you have RP and you have RN. And this is V out. So we know how to solve this, right? Resistor divider. I figured it out after last class. So Rn plus Rp times VDD. Right? That's the general equation of a network like this. So now what's happening, depending upon the input signal, we're going to either make Rn much smaller than Rp, or Rp much smaller than Rn. Right? That's really what we're doing with the switching. And in the ideal case, when the transistor is off, actually the size of the resistor should be infinity. Okay? But you can see that when Rn is much smaller than Rp, we're going to get here, you evaluate this here, it becomes a very small value over Rp, it gets close to 0. So you get V out is approximately equal to 0. Okay? On the other hand, when Rn is much larger than Rp, in that case you see that Rp drops out and you get approximately something which is equal to 1. So V out is approximately equal to VDD. Okay? So that's the basic operation that we're looking at. We're modulating the resistances of the transistors. And in order to get a good noise margin, you would like to, as you can see, we would like to make sure that the Rn and the Rp in the different steady state modes have a orders of magnitude in difference between them. The bigger the difference between Rn and Rp in mode 1 or mode 2, the better. The clearer we're going to be close to 0 and VDD. Okay? So that's all. This kind of whole thing we discussed in last lecture kind of summarized, and then we add a capacitor to this and we can compute the propagation delay, we can do a first order power analysis, we can do a first order type of static power dissipation analysis. Okay? Alright, so let's now go back to the manufacturing process. I kind of briefly walked you through this whole procedure last time around. Right? The state would really the secret, or the big central secret of CMOS or semiconductor manufacturing is this photolithographic process. The fact that we use masks with the patterns, and we use light to basically project those patterns onto the substrate, silicon substrate, and repeat this over and over and over again. And The nice thing about this is every time we do a particular step, we print billions of patterns simultaneously. Okay? As I mentioned before, we have one particular problem with this process is that obviously light has a certain wavelength, right? Remember that from some of your physics classes, right? So you think about light that's already kind of going at the violet space at the very high frequencies. Wavelengths are sitting around 200, 130 nanometers approximately in the visible light spectrum space. Okay, let's say it's 100, 130 nanometers. Now the problem is we're trying to, if we start doing 65 nanometers or 90 nanometers, you can see that the dimensions I'm trying to print are smaller than the wavelength of this light. So you can imagine that it's getting quite complex for me to basically print very precisely 22, 35, or 40 to 45 nanometer patterns if I only have this wavelength of light. So you say it's actually impossible, right? You have something which is, as I compared to last time, you have a very thick brush, and I try to paint with it a very thin line, precisely and repeatedly. Tough type of thing to do. So you say, well, why don't you use smaller wavelengths for the light? Why don't you go to other type of frequencies, higher frequencies for the light? And you can do it, and people are trying. There's now a lot of effort going on in what's called extreme X ultraviolet, EUV it's called. Turns out not to be too simple. People have been working on it for the last 10 years, and they still haven't solved it out completely. But this is the solution that a lot of companies are thinking about when they do 22 nanometers type of technologies. There's also other people have been trying to use X-ray. X-rays are, again, these are basically electromagnetic type thing with very small wavelengths. But our X-ray has its own problems. The main problem with the EUV, for instance, is that you have to have a huge amount of power to project in that light beam to basically be able to put it into patterns correctly. And so there's some big power problems. Now, so we don't have a solution yet. So you might ask yourself is how have people kind of managed to do this, stick to 130 nanometer wavelength for your light and still be able to print 65 nanometers? And we do. We do it all the time right now. Well, engineers are smart. What they have been coming up with is a number of things. One thing is, for instance, you can actually have multiple phases of light. You basically change the phase of the waveform. So and you use actually multiple phases of that light to project the pattern a number of times. And by doing so, you can actually get even more resolution than you would get with just a single projection. That's one. Number two, what they have done is the following thing. So, well, gee, if I use light with a long waveform, I might, for instance, let's assume that I try to print something like this. Right? Nice little pattern. If I just use 130 nanometer to project this pattern, which maybe is, as I said, this might be 65 nanometer thick, what you end up is something which is going to look like this. And it's going to get rounded at the edges, and the middle, everything is going to get thinner. Right? So obviously this is not going to be very good. If this is supposedly going to be your transistor, you have a problem. But what you can do is pre-distort it, because we can project, we can compute. This is physics after all, right? You know how light basically interacts with the mask in between and how it curls around it as a waveform. So we can do the opposite transformation and pre-distort the mask. You say, well, gee, I'm not going to design a mask like that. Maybe I'm going to take a pattern like this. And if I put light to this, I'm going to end up with this nice little squarey thing at the bottom. So you do pre-distortion of your mask in advance. Now, it sounds easy, but think about it. You have a billion of those patterns, and they interact with each other. Right? You have a whole bunch of things in the neighborhood. This is a massive computational problem, which is nice because we have fast computers. So that's exactly what they do. That's why mask making is so expensive. These guys are sitting there for running a couple of days, a whole bunch of arrays of computers simultaneously to do this pre-distortion type of function. And nowadays, they actually do even more clever things. The latest thing is they still use optical lithography, the same thing, standard waveforms, 130 nanometers. But instead of putting the wafers in normal open conditions, they put it in water. So you have your mask, you put water in between, and that's where your wafer material is. You use actually a material with a different refraction coefficient. Again, lets you do more precise type things. And now a lot of companies are trying to do oil. So you actually use something which has a larger viscosity to put in between as the intermediate signal between your light and your projection surface, which is basically your mask. Okay, so interesting problems. A lot of things going on in that space, but still, the bottom line is we still use lithography as the main way for us to print basically patterns. Okay, and it's always the same thing. You put some layer down, then you project your patterns on it. You develop the resist. So the things that were exposed behave differently than the ones that are not exposed. You etch the things, either dry or using some of those viscous acids. And then you develop them and you do the next step. So, and you do this over and over again. So let me give you an example, for instance, of how this could work. So let's assume that I just want to put down a number of areas where I want to have thin oxide, silicon dioxide. So you start with your base silicon. Then I grow in the oven a thin layer of silicon dioxide, just by basically streaming oxide on top of the silicon. All of you who have done 143 probably have done something like this. And then I put a small layer of photoresist on it. We put the mask over it and put it in the stepper and shine light on it. So you can see that the areas where there's a pattern on the mask don't get exposed. Where there's no pattern, light just goes through and basically develops or exposes the resist. Next thing is develop that resist, so you harden it in the places where it's exposed, and we do etching. So etch away first of all the resist. The hardened resist is basically etched away, and then we use some other material, for instance, you can see here, you still have the resist, the hardened resist. Now if I come in with, let's say, an acid material, you can see here in the places where there's no resist, nothing happens. So where there's resist, nothing happens. In the other area, we just etch away the silicon dioxide. Then I remove the resist using some other liquids, chemicals, and we end up with a very nicely patterned silicon dioxide. And we could do the same thing with polysilicon and other things. Like, for instance, now I have a hole here. I can say, well, gee, if I now put the mask here, I can start putting an ion planter, for instance. I want to get some diffusion. I shoot some ions at it at high velocity and high energy and shoot them into the substrate, and suddenly I might be able, for instance, to create a P+ material or an N material, depending, or N+ material. So we can do diffusions once we have patterned the layers above that. Okay? So that's just an example of that. Typically, that's the way you're going to do the early steps. Is you build your silicon, you put silicon dioxide on it, and then you diffuse, you implant, you put some oxides down, you put some polysilicon down, and so on and so forth. The higher levels of the process are done differently. What you do is you take your wafer, and every time, for instance, we use some deposition methods to put metal down. Let's say you have vacuum deposition, you put a whole bunch of metal ions, and they float around, and they deposit themselves, form a layer. But then we use, again, etching and masking and lithography to put patterns in metal and etch it away where you don't need it. Same thing with the dielectric materials. In between there, every metal layer, we're going to put a dielectric material. So you get very complex patterns. This is a picture actually from IBM, which is pretty amazing. It's copper-based interconnect. You can see it at the red color, where they have etched away all the dielectric material. So you can see that this metallization stack becomes quite complex. This is layers and layers and layers and layers. It's like a apartment building with 10 floors, kind of approximately. That's what we're building today. And newer processes keep on adding more and more metallization layers. As I mentioned before at the end of last class, we used to use aluminum for this, but today we use primarily copper in the more expensive and high-speed processes. Why? Sorry? That's right. Copper is one of the better conductors. Aluminum is not bad, but it's not the perfect conduction material. Copper is a lot better. Copper is even better than gold. People have been using gold quite often as well, but it gets kind of an expensive thing after a while. He's keep on putting more and more layers of gold and diamond on it. No diamond. So the best one actually would be silver. But silver is a very tough material to work with. Even copper is a tough material to work with. It was a good reason we kept on using aluminum and not copper, because copper tends to interact with silicon. You put copper directly on silicon, some of the copper atoms and molecules tend to diffuse into the silicon. They kind of poison it, as you look at it this way. So you have to make sure that you never put copper directly in contact with silicon. And this is what this process that IBM invented, called the dual Damascene process, is all about. Actually, the copper has always a little thin layer of other material in between, in such a way that the copper is never in direct contact with the silicon. And this way, we can now build this very nice copper type of patterns. So this is the way a modern CMOS process looks like. This is called a dual-well, shallow trench isolated CMOS process. A lot of words in one thing. Let me explain a little bit. Obviously, when you do CMOS, you're going to have NMOS transistors and PMOS transistors. One option we did for a long time was to say, well, gee, I'm going to take let's say I take a P substrate, okay? You take a silicon layer of substrate that's P doped. Then we grow in certain areas where I want to get PMOS transistors. I'm going to put down and diffuse or implant an N-well region. So you make a material in that P by putting large implantation there. You make it N dominant. Okay. Now you can see this in this N-well. I can put P plus diffusions, put some gate down, and I have my PMOS transistor. For the NMOS transistor, it's kind of straightforward. We just have, this must be N plus. So this is N-well. So again, this is an NMOS transistor. Here I can just put P plus, and I basically get my transistor, my PMOS transistors. So the PMOS transistors are directly implemented in the substrate. For the NMOS devices, I have to put a well down. Okay? That's the way it used to be done. Today, however, if you look at this process, a little bit different. We start with P plus material, and then you put down a layer of what's called P-epi. It's a P-based material. Okay? Now, for both NMOS and PMOS devices, we're going to create separate wells. Like this is a P well, this is an N well, which you dope with a particular certain level. So now we have individual wells for both my PMOS devices and my NMOS device. So nothing is directly implemented in the substrate anymore, as we used to do. Okay, that's the difference between the two. So you create wells, N wells for N plus for your NMOS transistor, P wells for your PMOS transistors. Okay. Let's see what else is there to be seen in this picture. As I mentioned before, you have to isolate the devices from each other. We have to be able to make sure that our PMOS transistors, the source and the drain of those don't mix together with them. NMOS device or that neighboring NMOS device don't mess up with each other. So we put silicon dioxide insulation between the two. It's like a barrier. It's like we call it a trench. What you really try to do is kind of create a stopper of silicon dioxide. You etch it in there, and then you fill it up with silicon dioxide. So this way, electrons and holes cannot cover that easily from one to the other one. They're basically blocked from each other by an insulator. That's what we call it, a trench-isolated CMOS process. You dig trenches, like with a shovel, and you put basically silicon dioxide in there, and that's the way you separate things out from each other. Okay? So what else is there to be seen that's different in this process than a general process? So obviously, when I want to make a particular transistor, like an NMOS transistor, we take implant N plus devices, create our source and drain diffusion areas, and then we create a gate oxide right here and put a polysilicon on top of it to basically create a gate stack. Right? So you have polysilicon, silicon dioxide, N plus, N plus. All of that done in a P-well type of region. Okay? Now, What is there interesting? There's a couple of other things that you should notice. There's also that purple stuff. Can you see the purple things? Light violet, like pinkish purple, right here, here, and here. This is actually titanium silicide. It's a silicium kind of based, silicon-based type of material, but it has a mixture also of titanium into it. It's a compound molecule of titanium and silicon. Now, the reason we put that down there is very clear. Let's say your P plus region, right? Or your N plus region. That's my source contact, my source region. Now, if you make our transistors smaller and smaller and smaller, turns out that the resistivity of that region becomes more important. That you start seeing that those regions actually start having a fairly large resistivity connected to it, which is not very attractive. It means that in series with your source and drain contacts, I'm going to have a resistor, kind of, if you look at it from a modeling perspective, which is going to slow down your devices. And there's very little I can do about that, because the drain, the doping levels and things like that are fixed. The sizes of your source and drain are basically fixed. So that's why we put basically that silicide on top of it. It doesn't really interact with the transistor per se. The transistor is still the N plus channel in between. But the silicide are sitting over the source and drain regions, basically reducing the resistance. It's like a parallel path that I'm providing for the electrons to flow. And as a result of that, I reduce that source and drain resistance. Okay? The same thing we do with the gate. If you look at the gate stack, you have the polysilicon. And we use polysilicon because polysilicon goes very nicely together with silicon dioxide. They like each other. Other materials don't connect that nicely to your silicon dioxide. Polysilicon does. They have a perfect bond between the two, with fairly little trapped states. Now, polysilicon is what it says, right? It's a polycrystalline version of silicon. Has a resistivity which is not very good. It's not as bad as basically diffusion, but still the resistivity is way worse than, let's say, metal, aluminum, or copper. So we see now that you also get a resistance in series with your gate. Your polysilicon brings in the signal to the gate. It has resistivity as well. By putting some sandwich of material together, it's like a sandwich. You have polysilicon and you put titanium silicide on top of it. You get two layers, one with low resistivity, the one with a higher resistivity. But if you put two resistivities in parallel, you know what you're going to get. You get a smaller resistance, right? Yes?
Not sure what you mean by those two being in parallel. Looks like it would be in series, right?
No. So if you look at it, right, so you have your polysilicon. And think about this is a 2D plot. In reality, it's something like this. And then I put a second layer of material on top of it, connecting to the same ends. So what I have here is resistivity of my polysilicon in parallel with my resistivity of my silicide. And if you look at the overall resistivity of the two, it's going to be smaller than the resistivity of the smallest one. So that's the advantage of this approach. Series would not be very nice. Yes? At one. No, but let's come back. Let's come back to that other picture. Might have another picture here. That's 2D. Remember that 3D picture I had last class? I don't have it sitting right here. We can try to sketch it. 1 second here. Let me erase. Remember how the transistor looks like in reality? It's a square. Right? And you have some insulator. You basically insulate all around it. You have silicon dioxide as stopper. And then you have here your, you create somewhere, this is going to be diffusion area. Somewhere you have a thin layer of silicon dioxide. So this is going to be diffused to N plus, N plus. This is silicon dioxide. And then I put my polysilicon over it. And this comes a wire which kind of runs off. So this is your polysilicon wire forming your gate. This is the width of the transistor. This is the length of the transistor. Okay? So there's only one contact to this thing, right? It's basically something that brings in your gate signal from the side. But it's basically two, instead of using one layer, you basically sandwich two layers on top of each other. And as a result of that, you get a small resistance. Okay? So you can also see how we built the metal stack. So you have your different metal layers. It could be tungsten or could be aluminum, copper. People use a variety of things, or copper or aluminum or combinations. So you have layers of those. As we saw in the previous IBM picture, you see this layer, next layer, next layer, next layer. We pattern them, obviously, and then put silicon dioxide in between as the insulating material. But obviously, I have to be able to traverse from one layer to the next one. That's why we have those thingies here, which we typically call vias or contacts, depending on what layer we're talking about. There are like little holes in between through the silicon dioxide that brings metal from one layer to the next one. It's a connector, basically, that goes from layer to layer, just like you would have in a printed circuit board. Like, for instance, here you stack two of those vias on top of each other. I can go from this layer right away to the source of this transistor here. Okay, so this is what's called a stacked via. You put them on top of each other. But remember, these holes are very tiny. Contacts are basically on the range of a couple of 100 nanometers. And to make a good contact, you would like to have the resistivity to be quite small, so you have to make sure that the whole hole is filled up with metal. If it's only half filled, like you start basically growing that metal, if it's only half filled, you will have higher resistivity. You don't want to have that. Okay? So a lot of tricks involved in building a process like that. But it's important that you kind of see this. I think one thing is important that you learn from all this is that you can start seeing a multidimensional vision of how a layout looks like. Typically, we always project this in a two-dimensional way. Right? We're looking at our masks, and that's the way we look at a design. But very often, if you want to see where the capacitances come from and how crosstalk between wires can work, you have to be able to project this in a 3D space. Kind of look, hey, this wire runs next to this each other, and it's actually quite thick. So you have two wires running like that next to each other. Maybe there might be some capacitance that sits in the sidewalls. But you only can see this when you start visioning in a three-dimensional fashion. That's why this is kind of important. So let me translate this. So this is, yes?
Why does it matter that the resistance at the gate, if like the gate usually it's just kind of like in a circuit, it's not connected to anything. So
that's a very good question, right? So your gate is a capacitance, right? It's a capacitance, and you connect into it. So why would you care about resistance? That's what you're asking. And you're right. From a DC perspective, I don't care because there's no current flowing through it. I do. But during the transients, it does. So I have an incoming signal. So suppose I have a CMOS inverter. So as you said, basically, it's purely you're looking into your gate. There's no current flowing in it. So there's no DC current. But if I would have a resistor in series with this, and you can imagine the gate, if you look into the gate of a transistor, you see capacitance. So what I'm creating here is an RC time constant. RC time constants always mean the same thing, delay. It's going to make your gate slower. It's going to take you a longer time to charge up that capacitor or discharge this capacitor. And that's why we don't like to see a large resistivity on the gate of a transistor. But it was a very good question. Okay. So again, here's our 2D perspective of the transistor. In this case, is an NMOS transistor. So we have N plus implants into a P well. For a PMOS, we do the opposite. It's P plus implants into an N well. So this is your cross-sectional view, right? But it's very rare you're going to see a view like this. When you do layout, you're going to do just the opposite. We take a top view in some sense. So we say, well, gee, what I need to design a transistor is I need somewhere an N plus region, another N plus region. Actually, this whole thing is going to be what's called active area. We put polysilicon on top. So this polysilicon over diffusion typically will create what's called a gate, right? Because I have N plus here, we will have a gate in between. So you have a poly mask, I have a diffusion mask, then I need some contact masks to be able to contact to it, and then I have a metal mask, and the wires come in and out. So you have my transistor. This is the source, this is the drain, this is the gate. This is the view we typically will see from a layout perspective. You look at every layer from the top perspective. Okay? And by the way, this is my P-well region. And outside this P-well, I'm going to have this. This region here where you don't have diffusion, where we have P-well, I'm going to have silicon dioxide stopper. Right, as you can see in the top view. You can always go one from one to the one you see here. This edges here coincide with the silicon dioxide stopper. Okay? But it's important occasionally because if we just look at the top, it's very hard to see where capacitance come from. For instance, you can see here that if I have a channel, like this green channel here, this channel interacts with this silicon dioxide right here. So you can see there's a sidewall sitting around the side here. Around your whole source region, on the side they're going to have silicon dioxide, which might add to some capacitance. Because you have an active material, a conducting material, you have a dielectric, you have some other conducting material on the other side, you might see a capacitor there. Right? That's something you can't see at all from this two-dimensional top-down projection. It doesn't give you that vertical dimension to it. Okay? All right. So this is what you're typically going to do as a designer. You're not going to design that three-dimensional structure. Now what you're going to do is create those different layers. So, well, I'm going to have to make active area. Active area is where I build my transistors. That's where I'm going to have source and drain regions. But also gate regions, because the way we're going to create the silicon dioxide is put polysilicon over that. And we know that under polysilicon, I always would like to, if you have polysilicon over diffusion, underneath I would like to see a silicon dioxide. Right? So this creates a gate. Anytime I put polysilicon over diffusion, I get a gate. I get a transistor. Okay? So polysilicon is an important mask, typically shown in red. Active area, depending if it's an N plus region or a P plus region, it might be green or brown or different colors, it depends. Wells, you have to design the well region. I have to be able to put down different metal layers. So you have, for every metal layer, you have particularly a color, like blue or magenta or some other colors. Can you imagine you have 9 metal layers, you have to have a lot of colors. And then you have to have the contact holes, which is these holes that go vertically through the stack. And that's typically what you do when you create a layout. You're going to basically be drawing patterns on those different layers. And by choosing how they interconnect with each other and how they overlay with each other, you create transistors or you create an interconnect network. Okay? So that's the art of design. And there's actually really nice tools that allow you to do things quite easily. We call it layout editors. It's like one of your graphical programs, like draw programs or anything like that. But it helps you to put down transistors a lot more easily, repeat patterns a lot more easily, do fairly complex type of things. That's really what a layout editor is all about. And you will definitely work with layout editors in this class. Okay? In a 0.25 micron process, these are the colors we choose, but that's not that important for the time being. Now, here's the set of layers that I have. You know, they're always going to be the same. You have polysilicon, you have diffusion, you have well contacts, you have vias, you have metal 1, metal 2, metal 3, and so on and so forth. So how do I now know what I'm allowed to do? Can I draw patterns in triangular shapes, circular shapes, whatever? How close can I put the wires? What's the distribution of the wires? All these type of things are valid questions to ask. Well, obviously, in order to be able to fabricate something, the fab will tell you, hey, wait a second here. If you put wires too close, there's a good chance that they're going to be short circuited. Or if you make them too thin, they might disappear. There might be an open circuit happening. So this is what design rules are. They say, well, gee, your minimum width of wire should be this, at this layer. Or if you want to make sure that two wires are not connected to each other, you have to put them a certain distance from each other. And if you want to get a transistor, there's some other rules between layers. Like I have diffusion or active area, and I have polysilicon. There's some relationship between the two that I have to put the things down to get a working transistor. This is what we're calling design rules. So as I said in this slide here, it's kind of it's a contract between the designer and the fab. The fab basically says, if you do it that way, we'll do our best to make sure it works. We cannot guarantee it, because there's always yield issues and so on and so forth, but we give you a very good bet that it's going to work. Okay? So it's a set of guidelines, and from those set of layers, you design all those layers, then you ship it to the fab or to the tools, and the tools are going to generate the masks for you from that. Okay? Typical today is that all of your rules are going to be given in absolute dimensions. It says the minimum thick of a polysilicon wire in a 65 nanometer process is going to be what? 65 nanometers. Right? The maximum, there might be sometimes maximum thicknesses. There's a variety of things like that. Okay? Now, things are not getting easier. I can tell you that. You can imagine now when we start doing this very dense connectivity, I will still use this 130 nanometer light waveforms. You can see some interaction. If I put patterns too close of very weird shapes to each other, they might start interacting with each other. So my pre-distortion of my mask might not work anymore. So the bottom line is that the more we go down in feature size, the more complex the design rules are becoming. Life is not getting easier for a designer because of a bunch of reasons like this. But let me just show you a couple of those design rules. There's three classes. There's intra-layer, interlayer, and then some special rules that we're not going to talk much about it, but it's like density rules. Let me give you an example of that. The way we do metallization, right? You put down your metal, you grow it. So let's say I have dielectric, and I put metal down, and then I etch it. So I get a bunch of wires. Okay. Then I do some. Then I put silicon dioxide on it for the next insulating layer. Now you can imagine, if I grow silicon dioxide, what would you get? Something like this, right? You grow this, or you deposit this, or you grow, or whatever you do, or you do wet deposition or something like that. You're not going to get a flat pattern. And then I put the next layer on it, and you can start seeing weird things happening. And you can see that your surface is going to get worse and worse while you go higher and higher. And obviously it's not going to work. So what do you do? People had a big problem with this. For a long time they didn't know how to put multiple metal layers down because of exactly this problem. Till somebody figured out a very crude methodology. So what do you do in the real world when you use power tools to flatten out a piece of board or something like that? You sand it. You take a sander and you go you abrasive techniques to flatten it out. That's exactly what they say. Hey, let's try this on a wafer too. It's basically it's called CMP, chemical mechanical polishing. What they do is after they put down this thing, they kind of polish it out with like sandpaper almost, and then they do the next layer. And this way you can make sure that while going up, you planarize things always continuously, and you can keep on going. Now you can see that if I now would have a layer with only one metal wire, and then I put my silicon dioxide on this thing here, and I start planarizing, you might have some interesting effects happening. You might actually brush your wire away if you're not careful. Or the density or the thickness of the wire is going to be a function of the density of the number of metal wires that you have. So that's a problem. If you have something which occasionally I have something, it's a lot harder to planarize it than when you have a very irregular pattern continuously. Right? So this is what's called density rules. The fabs require to have a minimum number of features per layer. Let's say per square centimeter or per square millimeter there has to be so much should be covered by metal. So what you do is just do dummy little piece of metal. They don't do anything. They're not connected to anything. They just fill up the layer. That's what we call the density rules. There has to be so much metal. So you have tools that automatically fill up all your blank spaces with chunks of metal that are not connected to anything. And this way we can planarize things nicely, and we get very, very predictable widths of your wires. So that's some of the design rules. Typically in this class you don't have to worry about it. As I said, there's automatic tools for this. Towards when you're done, and at the end of the design, say, okay, planar, full up the density, make sure I meet the density rules. Okay? What you care about is those two here, intra-layer and interlayer type of rules. So let's look at them. Here's the intralayer rules. Well, for instance, I take polysilicon. What it says is I have two polysilicon wires. There's a minimum depth of a polysilicon wire. Okay. What I use here to express my dimension, I use something which is called the lambda dimension. And lambda is going to be equal to the minimum feature size of a technology divided by 2. Okay? So if I do a 65 nanometer process, what's my minimum feature size is going to be 65 nanometers. I cannot do anything thinner than 65 nanometers. Now, if I would use that as the unit, I have a problem. I only can do multiples of that. Right? I could only have minimum feature size, 2 times minimum feature size, 4 times minimum size, and so on and so forth. So what we very often do is, well, gee, we're going to use half of it. Then I can have something which is minimum feature size and 1.5 times the feature size. Like metal 1 here has 3 lambda as width, which means it's 3 times minimum feature size over 2 is 3 halves, is 1.5 times the width. Okay. That lambda rules used to be very popular. More and more now we start using, say, well, gee, I'm just going to put here 65 nanometer. And forget about these relative dimensions. Use absolute dimensions. But anyhow, this slide uses lambdas. That's why I had to explain this. So what it says is a polysilicon wire has a minimum thickness of 2 lambda, or 0.65 nanometers. And you have to separate them by 65 nanometers. Minimum separation. Metal wires, on the other hand, you can see are not going to be as dense. They have a minimum width of 3 lambda, which is approximately 90 nanometers, and they have to be 90 nanometers apart. And what you will see is the higher I go in the metallization stack, the fatter the wires are going to become. The minimum thickness of those wires getting fatter and fatter and fatter. We'll explain later why I won't like to have fat wires and thin wires. But bottom line is, you go higher up in the metal stack, wires are going to be pushed further apart. And the minimum feature size is going to increase. Same thing with active area. Remember, active area is where I get diffusion. Right? So we design a transistor by putting active area down and overlaying it with polysilicon. Same deal for active. Let's forget about the select layer. We're not going to use this in this class. Active layer is your diffusion. Says the minimum width of a diffusion is 3 lambda. Separation is 3 lambda. We also have wells. You have to create well areas where you're going to put either NMOS. You can create a well area, so I put a couple of NMOS transistors there and a P well. I create an N well area, put a bunch of PMOS devices in there. There's some rules about wells as well. As you can imagine, remember, wells are separated by that silicon dioxide trench. So there's a minimum separation required to be able to build a good trench. So it's either when you have a well, 2 wells that are sitting at the same potential. Obviously, when they're the same potential and they're the same well, this is N well, let's say, this is N well. I either can connect them together, but if I don't connect them together, they have to be at least 6 lambda apart. Okay? If they're on the same potential. However, if one of them is 1 voltage and the other one is another DC voltage, they have to be at least 10 lambda apart. So wells take quite a bit of space. You can see you have to push them aside quite a bit. This is wasted area on your chip. So very often what we try to do is create 1 well and put as many NMOS transistors into this as possible, rather than create a new N well for every transistor, because that's waste from an area perspective. Okay? So we see on every layer, well, active area, polysilicon, metal 1, metal 2, and also contact holes, we have minimum dimensions. Contact hole is really what it is. It's a hole that you basically etch through the silicon dioxide and you fill it up with metal. Okay? So that's the intra-layer design rules. Then we also have the intra-layer. These are the interesting ones. That's where one layer interacts with the other one. And in general, there's 2 important regions for those. 2 reasons why we have intra-layer interactions. It's number 1 is transistors. Number 2 is to create vias and contacts, right? Obviously, when I create a via, I go from one layer to another layer, so there's some interaction between those layers. Obviously, if I go from metal here and metal here, I better make sure they overlap with each other. If they don't overlap, the chance that my via, my hole, is going to connect to both of them is going to be very small. It's 0, actually. So here's a typical transistor. So this is your diffusion. And we know the minimum width of this diffusion is 3. Remember that previous slide? Minimum width of your polysilicon is 2. So I create a polysilicon stretch here, and that's here where the polysilicon overlaps with the diffusion. That's where I'm going to get gate oxide. That's where I basically get a transistor gate channel. Okay. Now there's a couple other rules that you have to keep in mind when you build transistors. Number one, you see this is going to be N plus region, right? This is source or drain. There's a minimum size of your source or drain regions in terms of the length here. Okay. This thing is set by the minimum width of your device. Remember, diffusion has to have a minimum width of 3. Okay, so this is setting the minimum dimension this direction. This sets the minimum size that you basically have to extend from the gate to basically the end of the source or the drain regions. Right? For instance, I could not make, I say, well, sometimes I say, well, I would like to make a smaller source. That's not allowed. You have to extend at least 3 out of there. So this is my region. This is my drain region. Now, sometimes I like to make the corner like this to make it easier to connect. There's a rule that says that this diffusion here should be at least 1 away from your polysilicon. Even though they're on different layers, we still want to make sure they separate the edges a little bit. Now, you can imagine why. All right, think about this diffusion region. Here, this whole yellow area, where there's no diffusion, is going to be silicon dioxide. It's this thick trench. So you can see here now, if you look at it in a two-dimensional fashion, you have your well region, or your active region, and all of the around there, we're going to have this silicon dioxide, which is a thick thing that kind of stretches up. Now, if I put polysilicon too close to the edges, it's going to sit on that side of that wall and might break off. So you have to make sure that if you have put polysilicon like here, like for instance, this little piece of polysilicon of the gate has to extend at least 2 lambda outside of the diffusion region. So why not just stop here? Why have this little extension? Well, you can see here that's at your edge of this little sloping part, your silicon dioxide seat. Here comes your polysilicon, and now you have your sloping end. If I would just stop right here, you have a tricky part. You might go a little bit too far, or not far enough. So you obviously have to make sure you extend in this region. But if you don't expand far enough, you have a little piece of polysilicon that sits on the side here. Good chance you're not going to be able to produce that reliably. It might break off and short circuit the other part. So we're always kind of requested to go over the polysilicon, over the silicon dioxide, and go to the top. So you have this nice connector that basically extends outside. So this is why we have all those extension rules, like this one here, this one here, some separation rules, like the 1 lambda between the diffusion here and the polysilicon. Okay? Now from this already, just looking at these design rules, I can know what my minimum size transistor is going to be at. Right? Remember, we can size transistors from at least 105 or 40. You know that we can size a transistor by changing the length of the transistor or the width of the transistor. Now think about it. If they can say, let's say I do a 90 nanometer technology. What's going to be the minimum length of your transistor? Yes? That's right. It's 90 nanometers, right? So you basically think about this. It's going to be determined by the width. So this is your channel. Channel length is defined here. It's going to be determined by the minimum width of your polysilicon. And the minimum width of your polysilicon is typically the minimum feature side of your technology. So we say 90 nanometer technology means I have a transistor that has a minimum length of 90 nanometers. How about the width of my transistor? Can I also make it 90 nanometers? The width of the transistor is this dimension. Right? Here you have your source. This is my drain. This is my gate. So what's the minimum width? Oops. Any idea? That's correct. 135 nanometers. Because remember, the minimum width of diffusion is 3, which means 1.5 times the minimum feature size. So 1.5 times 90 nanometer is 135. So I never can beat a transistor which has a W over L of 1, which is minimum feature size. If I would create a W over L of 1, I have to make the length of the transistor larger than the minimum size. Okay? So this is what we're typically going to call a minimum size device. Is a device that has W over L of 3 over 2. Okay? This is going to come back quite often. We're going to say use minimum size devices. That's the device you're going to use. Okay, so that's one example of interlayer design rules. Here's another one. This is the other area where we connect things together, is when you create vias and contacts. Now you can say, well, gee, if I would do something like this, I have a metal 1 wire, and I have a metal 2 wire, and I have some overlap here. That should be sufficient for me to basically make a hole here, stretch this whole thing, and make this as a via. Right? That should work. Well, the probability of this working is quite small, because you might have some misalignment between metal 1 and metal 2, and also your hole might be a little bit misaligned. So the chance is that your hole might end up there, and the wire is shifted up a little bit, and so on and so forth. That's not a good thing to do. So what it's typically going to require is that metal 1, if you want to make, let's say, a via between metal 1 and metal 2, we're going to require that the metal 1 is that there's some extension on the sides of the via, on the hole. So we take metal 1, and we're going to make some extension. Let's say this is 3, say this is going to be 4. We're going to have a minimal area of 4 for the metal 1. The same thing we're going to do with our metal 2. We require a minimum size of 4 that we overlap with the other one. And then we place a 2x2 contact hole in the middle. So now you can see that a via is formed by a piece of metal 1 overlapping with a piece of metal 2, and a via somewhere placed in the middle, or a hole. And in order to make it work, you can see there's some extension rules. Here's my hole, and I have to extend one lambda on all the sides of that hole in both metal 1 and metal 2 to make it work. Okay? So that's one of the rules. There's a bunch of other rules, how close vias can be to each other. For instance, they have to be separated by 2 sides if you want to make 2 holes. If you want to make a big contact, I can either do, I'm going to take a giant piece of metal 1 and a giant piece of metal 2, and then I make a really big hole in the middle. Right, then fill that up. Well, unfortunately, the fab won't let you do that. There's a minimum size of the hole. There's also a maximum size of the hole. You can imagine, right? It's kind of, you're sitting there and you have your silicon dioxide and you etch holes into it. And then the truck comes by and basically drops down a whole bunch of metal on top of it. Now, in order to have equal filling, if you have big holes and small holes and you basically put a whole bunch of metal on it, you have a chance that, for instance, if your small holes are going to be filled up, your big holes are not going to be filled up very well, or vice versa. So to have an equal distribution of the metallization through the via and hole layers, we're going to make sure that the holes are approximately all the same size. That makes much better filling. It's going to give you better resistivity, better contacts. So there's minimum size and maximum size. Okay? And there's separation rules. Now you say, well, gee, I would like to make a big wire connecting to a big wire with very small resistivity. How would you do this? Well, I'm going to make a big hole, big piece of metal 1, big piece of metal 2, and rather than having one hole, I fill it up with little holes, like this. That's the way we make a big contact. You basically compose it of a whole bunch of parallel connections of holes through your different interconnect material, or the isolation material. Okay? So this is the way. Now, this looks very cumbersome, right? I'm, as a designer, I have to be counting there how much of those things, and I have to draw all those little black thingies. Fortunately, our CAD tools, our layout editors, allow you to draw. They offer something which is called a via layer. You just draw a via here, and have the via of this size here, and it automatically will put down metal 1, metal 2, and compute how many vias you have to have in there and put them in there for you. So it's abstracted away, which is a good feature, because otherwise it could be a lot of work. Okay? So there's some other interlayer things I mentioned already. The well and the substrates have to be apart. You have a well. I'm going to take a active area. The active area has to be a certain area or distance apart from the side of the well. Well separation, things we already talked about, and so on and so forth. So there's some other rules that come from this as well. But again, you learn this quite rapidly. The best way to learn about design rules is not try to look to a book and say, well, gee, metal 1 to metal 1, metal 2 to metal 2, all the type of thing. No, you go to this tool called the layout editor, and I think I have the picture right here somewhere. This is a layout editor. Just like iDraw or whatever tool you have, Visio, any one of those tools that you can get on a computer to draw things. But it's built especially to build polygons on different layers. Okay? So if you go to a layout editor, you can bring up very often a template which has all the different layers. And then you can draw a square in polysilicon, a parallel in diffusion. Like here in this case, we have, this is metal 1, this is metal 1. The red is polysilicon. You can see here the different well regions, or the active regions are determined by this green box. That's where my PMOS transistors are. This box here, it's kind of hard for me to see it from this end. Right here, you have the NMOS devices. You have the P well around it. We have contacts here. These are contact holes. And you can see here where you overlap the polysilicon with the diffusion, which is in purple, I get a transistor. Right? So you overlap polysilicon with, that's right here, this polysilicon overlaps the diffusion, I get a transistor, and then I put contacts in between there to make connections. Okay? Let me just remove all that mess again, so they can look again at the original. So you can see the regions where you have contact hole, you have metal 1, you have there's active area, there's well areas, and so on and so forth. And this is what we've drawn here is actually a 2-input. I think this is a 2-input NAND gate that we basically have designed. And you might not recognize it, but pretty soon you will be able to. Okay, so that's what you use. So you have this palette of layers, and then you select one color, you draw a box, you put another one, put it down, and so on and so forth. Now the question is, how close could I put things? Right, that's the design rules. How wide do I have to make it? Well, the nice thing about layout rules, layout editors, is that they are aware of the design rules. Somewhere you bring the design rules of the process in there. And then you can either do a design rule check. You run a little tool. It says, okay, here you go to the top here, one of the tools. It says, do a design rule check for me. And what it shows is pops up and says, hey, you look at this region here. It's going to mark it out, and it's going to highlight it. It says, this region is too narrow. This is too wide. They're so close to it. And it gives you exactly the reasons and the rule you're violating. So it allows you to do online checking of your design on the fly of if you're right or wrong. And this is the way you learn design rules. You start with 2 blocks and you shift them closer and closer together and say, uh-oh, suddenly you go wrong. I say, well, I shouldn't do this again. And it gives you the rule. It says, well, the minimum separation between this and the well, let's say here it says source drain active to LH has to be 0.72 micron. I'm too close to it, so that's no good. You have to redesign it a bit. You have to change your boxes moving apart from each other. The best layout tools that I ever knew, unfortunately none of those commercial tools does it anymore, is actually the one that did online design rule checking. When I basically put on my box, right away it would say, hey, wait a second, you're not allowed to make that box. And unfortunately, most of the commercial tools don't really have that capability. You always have to kind of trigger it yourself. Say, do a design rule check, and then it runs through your design and will show you where you have problems, rather than doing this on-the-fly guidance. Which is a pity. I still think this is the best thing to have. It's something that shows you on the fly what's going on. Okay, but you will play around with this. This is the cadence tools we're going to use in class. This is the type of tools you're going to basically be using to do your layouts in the labs, starting next week, and also in the project when we do some layout. Okay. Let's see if there's anything else to be said. So, but the bottom line is what you do in the end is, remember, this is your 2D vision of an inverter. What you do as a designer is translate this in this 2-dimensional set of overlapping layers. All right, again, I show an inverter here. This is my NMOS device, my PMOS device. This is my ground, VDD contacts, input, and output. Okay? So that's kind of summarizing everything that I wanted to say about design rules. Any questions about this? Now, you might think this is very complex, right? If you look at those drawings here, so you say, how in the world do they ever come up with a picture like this? Why not rotate it like that, and or move this thing a little bit farther apart, and so on and so forth? Or how should I put my transistors with respect to each other? It's a good question. It requires some skill. To do something, ultimately you would like to have a design that's as dense as possible, right? Remember, area is important. So you want to push your transistors as close as possible to each other, while still meeting design rules. And imagine now that I have said, oh, gee, design me a gate which has something like this, a 6-input NAND gate, followed by an NOR gate, and so on. So, well, gee, that's quite complex. How do you go around? So typically, what you're going to do is start with something like this. This is on paper. It's called a sticks diagram. It's a way for me to kind of visualize the location of my transistors without having to worry about the actual dimensions. And so, well, gee, I have to design an inverter. I'm going to come in metal 1. Obviously, I have to go from metal 1 to polysilicon because the gate is polysilicon by definition. Then I have one stretch of polysilicon wire. I'm going to have a stretch of P plus diffusion here. That's my PMOS device and my NMOS device, and then I connect to ground. And the output of this thing is going to be collected by taking those two transistors together and metal 1. So this is kind of a simplified drawing of your layout where I don't use the exact dimensions, but the topology is approximately correct. Like in this case, I'm using a straight line of polysilicon. My PMOS transistor is oriented in this direction. My NMOS transistor is oriented in this direction. And they're going to be placed on top of each other, and I'm going to use metal 1 for this layer, metal 2 for this one. And that's approximately how I'm going to position the wires with respect to each other. So this doesn't tell you exactly the size of the device, but allows you to envision how things orient and how they relate to with respect to each other. It's a very good practice when you start doing design, playing around with this kind of dimensionless type of artifacts on paper is going to be for the best approach for you to start learning how to do layout. Okay? This is called a sticks diagram for apparent reason. The transistors also look like thin sticks of the same dimensions. Okay? All right. So that gets us slowly but surely to the real inverters. Right? Here to show you, for instance, 2 inverters in a row. And this is a single inverter, CMOS inverter. Exactly like the sticks diagram I just showed you. Here's my polysilicon. It's one straight line. I have a PMOS device, NMOS device. They're oriented in this direction. I come in metal 1, and my output device is also then in metal 1. And I have my VDD and ground in metal 1 as well. So this is exactly as the device that I showed you in the sticks diagram, but now with real dimensions attached to it. Okay? I can then start repeating this. I want to get 2. Bingo, I just take the same thing and I keep repeating it. So building a 1,000 inverter type of chain is actually not hard. You keep on repeating it. You grab them, you do 4, you take an 8, and so on and so forth. So, oops. Oh well, I think I have to get another battery for this device. So let me switch for another. I have only 5 minutes left. So this, now I know exactly. I have about battery time of about an hour and 15 minutes on this. So we either reduce the power dissipation or we come up with a better battery technology, which is the right thing. I have another battery. Okay, so let me kind of wrap up this lecture with talking a little bit as an intro to the next lecture about the transistor model. Okay, so now you've seen how we design transistors, how we put transistors into our in our process, how they get fabricated, what the critical dimensions are. So all those type of things we kind of learned now. So we have now created a abstraction from the manufacturing process to the designer, so that I can start designing things in a very simplified fashion and pass it on to the fab. Now that's one good thing, but it's not sufficient. Right? If I wanted to design, there's another part that I need to have. I have to know how my transistors behave in that particular technology. I have to have a model that basically takes the physics of the device and hides them away in such a way that I can start designing things that will have a certain performance, have a certain speed, have a certain power dissipation, and so on and so forth. Again, I don't want to understand the physics. Like I don't want to understand the manufacturing. I just want to have an idea of how it works. Same thing with the physics, with the physics part of the thing. I don't want to be able to write down Schrodinger's equation every time I have to do the design of a single transistor. Now, what I'm going to do is try to model the behavior of this device as simple as possible model. Hopefully linear equations, but unfortunately that's not going to fly. Actually, they're going to be nonlinear. Darn, too bad. But we're going to have to live with that, and occasionally we're going to try to simplify it even so that we can do linear things. But we try to come up with the simplest model that when I use this to compute the currents and the voltage and things like that, that's darn close to what the actual device is going to do. Okay? So obviously, I can do different layers of complexity of a model. When I basically run SPICE, I would like to use something which gets very, very, very close to what your actual design is going to do. Fortunately, SPICE is a computer. They can deal with large, more complex equations. But then when I do something by hand, I do a first-order analysis. I would like to have simple equations that I can solve by hand, or just put them in MATLAB or something like that, and I come up with a nice solution. So we'll see that the design typically will involve different layers of models that we're going to play with. More complex ones to put in SPICE, and simple hand models for hand-level computations. And that's really what I'm going to go to right now and the next lecture. So let's think about a NMOS transistor. Right? That's the way we draw it. It's a three-terminal device: source, drain, and gate. Actually, as we will see secondly and shortly, it's actually not a three-terminal device, it's a four-terminal device. And because there's another contact here that connects a substrate, it's called the bulk of the transistor. It's something we're not typically going to use to put signals on, but it's an important contact because you can do some things by manipulating this voltage here. I can do some things to my transistor. Okay, but in general, we're going to consider a transistor as a three-terminal device. Most of the time, I'm also going to draw my transistors without the bulk contact. When I put, let's say, something like this to get like an inverter, you see here I use a three-terminal type of symbol for my transistor. I don't show the bulk contacts. What that means is that by default, I will assume that the bulk of my NMOS transistor is going to be at ground, and the bulk of my PMOS transistor is going to be connected to VDD. That's the default assumption. I'm only going to draw the bulk contact when I'm going to do some weird stuff. When I want to connect this voltage not to ground, but to something different. Okay? So, but most of the time, we're just going to let the fourth contact fall away. Okay? So, three-terminal device. And as I mentioned before, it's from a simplistic perspective, this looks like a switch. But obviously, it's not a perfect switch. It's a little bit more complicated than that. Okay? So in order to basically figure out the real speed of the device, real power dissipation, I'm going to have to come up with somewhat more complex models. Okay? The most important first parameter we're going to look at is the threshold, VT, of the transistor. As I said, it's a switch, and we assume that when the VGS, the gate source voltage of the transistor for an NMOS device, larger than VT, the transistor is going to be in the on mode, and when VGS is smaller than VT, the transistor is off. Okay? That's the first order part of our model. Now, you might ask yourself is what is causing the threshold of a transistor to occur? Right? An NMOS transistor typically will have a positive threshold voltage. Typical values, let's say your 90 nanometer process, around 0.35, 0.4 volt approximately. Okay? Just as an idea. You can change it, and there's different ways of moving it around, but let's assume right now between 0.3 and 0.4 volt threshold voltage. It means in order to turn a transistor on, I have to apply a voltage that is larger than 0.4. Now, you've seen all this thing in 105, for those of you who have taken 105, so I'm not going to do a whole bunch of explanation about how you do basically, right, about the work functions of the different materials and the band gaps and how you basically have to basically adjust those. That's not really what I want to go into. Bottom line is very simple. Threshold voltage of a process can be explained as follows. So I have silicon dioxide, and I have polysilicon. There's poly, and I have here P material. Okay. In default mode, when basically this is at 0, and this is at 0, and this is at 0, the transistor will be off, and what we see is that, first of all, this is P material, so it's hole dominant, but there's not many holes. It's basically not very heavy. So this is basically non-conducting material. Okay. Actually, it's even worse. Because of the difference in work function between the P and the polysilicon material, you will actually have here, at the top region, you will basically have a depletion region. It's going to push things away, and there's some region here which is going to be somewhat defunct of mobile carriers. So it's not conducting, there's no channel here. So what's going to happen? In 2 words, what threshold voltage does is the following thing. When I now start increasing the gate voltage, VG, I start raising this thing. You can say you get positive voltage here at my gate. Compared, this is going to be higher than my pole. This diffusion region will start to expand. It's getting, because positive hole, I'm basically pushing holes away. Put it this way, right? The holes like to go to the lower voltage, electrons like to go to the top. So the depletion region widens initially, but then suddenly what's going to happen is at a certain voltage, which we call the Fermi voltage, phi f, 2 phi f, phi f actually, we're going to see that suddenly by putting more and more positive voltage, I start pushing holes away. Actually, at some point in time, what's going to happen is my material starts to invert. It actually starts to become N-like material. You will see electrons appearing at the surface here. It's a very important point, right? Suddenly, from something which is totally non-conductive, you have a depletion region with no mobile carriers. Nothing is moving. And by increasing the voltage, suddenly I start creating mobile electrons in this region here. I create a channel which is conductive. Because now I have electrons here, I put a voltage between those two ends, those electrons will go to the larger voltage. And current will start flowing. So the threshold voltage is the point, is defined by definition as the point where I start getting this inversion. Where I go from a pure depletion to an inverted surface where you start seeing electron mobile carriers emerge. Okay? And that's our definition of the threshold voltage. Okay? And you can compute exactly when this is happening. This is when you really meet that point where you have this voltage at the surface reaches this phi f voltage. That's the point where we see that we're going to have minority carriers and electrons basically start to dominate, and the material becomes from P, it becomes N material. Okay? And this can be easily computed. There's equations for it, and you're going to have to trust me that those equations are right. I'm not going to derive them. I have no interest in deriving them. It's 105, it's 130 material. Okay? So that's what we're going to do at the beginning of next class.